Classmates, instructors, good morning, good afternoon, good evening. My name is Andre Williams. My presentation is designing a better data representation for deep neural networks and text classification. Most importantly, my presentation will be looking at two different approaches for text classification and applying what we've learned in class as far as ANOVA table and discovering statistical significance, applying those methods to see if there's a statistical significance between the two approaches. So here's an introduction of my presentation. In this study, we experiment to compare approaches for encoding characters to apply to convolutional neural networks for text classification. We're going to discuss the previous methods. I don't know how much experience you guys have to this, but we may be familiar with text blob, um, using text blob to get Twitter sentiments, or using Vader to get Twitter sentiments. We're going to discuss a few baseline methods to get sentiment analysis, and then we're going to go into the first experiment, the Zhang and Li approach, and then we will focus on the modified method that took the Zhang and Li approach and build upon that, and we will compare the two. Basically, we're going to compare the Zhang and Li approach and the experimental approach. Okay, a standard baseline method of sentiment analysis is creating a word vector that describes each instance through a presence of a word or the frequency of a word. So one of the well-known methods is word2vector. Word2vec is a machine learning process that uses word embedding to associate words with an array of numbers. This array allows us to use mathematical functions to find the Euclidean distance to create a vocabulary. So let's say if we have, if we were given a set of words, we can we can translate those to vectors and map those vectors to see which words are similar. As you can see here, you have lecture and talk here. These are similar, and they're very close to each other in Euclidean distance. You can see research and science. So we can use this to create a vocabulary to say. Now, word2vec has been combined with big data tools to learn semantic relationships, such as Paris is in France and Berlin is in Germany. So this is a very useful tool. All right, bag of words. Bag of words is also a commonly used method for text classification and sentiment analysis. Now, what is bag of words? Bag of words is essentially a machine learning method that tokenize words and process the frequency of each token, allowing us to infer more important words. Example, if we have an article that uses the word car very frequently, then we can assume that the article is about cars. Now, there are a couple of limitations, a couple of cons to the bag of words and the word2vector processes. Um, Now, one of the limitation is we can say that the English language has well over 150,000 words, maybe even more. Now, this opens up to a feature space that has high dimensionality. which can potentially lead us to overfitting. Another limitation is namely the loss of information. Uh, Another one is the bag of words approach does not preserve word order and other syntax. Now, how can we improve this? One way to improve on this is instead of creating models that learn words, we can create models that learn characters and make it infers it makes its inferences from the characters instead of the words, because the English language has, say, 100,000 plus words, but the alphabet has 26 letters, and you might have a couple extra characters for punctuation, commas, periods, question marks, parentheses, things of that nature, and that's just a simpler way of text classification and sentiment analysis. Now, classmates, this is where it gets pretty fascinating. The Zhang and Lacan approach for text learning tasks was that they used a convolutional neural network to train classifiers by representing a text as an image, and that's just mind blowing to me. But this enabled them to train a deep convolutional neural network for text classification tasks involving high level concepts. Their data representation employed one of M encoding, where each character is represented by a vector size of M, and we know M is the size of our alphabet space, or the characters in our alphabet. Now, we use this to create a sequence of text, and the sequence is created by converting each vector into columns of a data frame per se that visualize. It will create something like Braille, which can be accepted as an input into our convolutional neural networks. Now, this just completely outperformed bag of words and word to vector, and it gets even better. But this will be the first approach that we will use in doing our ANOVA analysis. Now, Zhang and Lacan encoded words into vectors where all elements are zero except those characters. Now, each vector is the length of your character space. So if you had a character space of 26, then your vector size would be 26. The length is the sequence of characters in the word. The sequence of characters encoded in this manner are similar to Braille. This is called one of M encoding. Now this will be the first method that we will use in our ANOVA table to see if the modified method is statistically significant from this method. Now here's a visual representation of that method. Now, as you can see, this looks like Braille or Morse code or something of that manner. But you can see this is, as we discussed, your vector is the size of your character space. So this is 1 of 256. So we have 256 characters in this Braille image. Also to note, I know it's hard. There's no segmentation in this picture, but this is pretty much a data frame. There are columns in this picture that gives us the sequence of characters to create a word or a character representation. Now, the modified approach, this is built upon. They basically used Zhang LeCun as a building block and made it even better by making the character representation smaller and more dense. Now, on the last slide, we had our Braille representation, which was a 1:256, but that's not very common in the Zhang and LeCun approach, because when you're using one of M encoding, the expansion of an alphabet from, the standard alphabet is 70 when you include all the punctuations, but extending that from 70 to 256 in a 1 to M encoding would require more memory, 3 times as much as memory, and a larger input layer for our neural network. You can just see here from our Braille representation on this slide, it's a lot smaller than the visual representation on the last slide. Now, this allows us to express characters in 8-bit form, or UTF-8, which is which is commonly used Unicode. This reduces the vector size from 1 to M to log of M. This is known as log of M encoding. Now, this is huge, because using this new character encoding, the resulting vector for each character is like 1/16 the size of the one produced from the 1 to M encoding for the UTF-8 alphabet. And this reduces the size of our data set memory by a factor of 16. So this is just huge gains here. And you can just look at the Braille representation here. You can see it's smaller in size. It's clearer. Less memory is needed. I mean, yeah, this is obviously a winner. Now, experiment time. The researchers in this project built a data set by randomly sampling 50,000 positive and 50,000 negative instances from the Sentiment 140 tweet sentiment corpus. This corpus contains like 1.6 million instances with positive and negative class labels. This also includes emoticons. Now, the log M encoding and the 1M encoding were both trained for 100 epochs. Both encoding methods were trained with an alphabet size of the standard alphabet size of 70 and an alphabet size of 256. And we compared the two to see which one performed better. All right, classmates, here are the results of our experiment using a convolutional neural network with 3 fully connected dense layers. Now, this is used with our data set with 100 epochs. We can see that we look at our first table here. We can see that we use the 2 approaches, log of M and 1 of M encoding. We use those 2 approaches with 2 different alphabet sizes, one size of 70, one of 256. Now, we can see here that the log of M method allows the network to be trained approximately 4.85 times faster than the 1 of M approach with an alphabet of 70. Now, the decrease in training time is obviously due to having a much smaller input into the neural network. Additionally, 1/16 as much memory is needed to hold the data set. So, yeah, there's that. We look at the average accuracy, and the log M method is more accurate than the 1 of M encoding method So how can we prove that this is statistically significant? Well, with none other than the beloved ANOVA table. So just because the results show that one is more accurate or faster doesn't mean that it's significant enough. So we perform our ANOVA table using the top three performers from our last table, which would be log of 70, log of 256, and 1 of 70. Now, the p-value, when we do our ANOVA table, you can see the p-value here is below 0.05, showing that there is indeed significant difference between the approaches. Now, after that, we do our Tukey honestly significant difference test. Here, this table here. Now we use, excuse my cross. Now we use this to determine significant difference between the approaches. Now, from eyeballing this, looking at it, you can see Group A, log 256 and log 70, are pretty close to each other. So there's no significant difference between those two. However, both um, both both approaches in Group A are distinct from the 1 of 70 approach. Now, using these results, it is safe to conclude that log of M is significantly better than the 1 of M approach. All right, in conclusion, classmates, this experiment showed and proved with the ANOVA table that log of M allows us to train a neural network 4.8 times faster. Additionally, we achieved significantly better performance with our network design when using log of M encoding compared to 1 of M encoding. But we also observed that using an log of M method with an alphabet size of 256 and an alphabet size of 70 resulted in higher accuracy. However, looking at our Tukey honestly significant difference table, we can conclude that there is that the difference between log 256 and log 70 is not significant. So feel free to use either one. However, both are significantly better than the 1 to M approach. All right, classmates, that has been my time. I found this material very fascinating, how we can convert words into Braille format and use CNN, which is typically used for image classification, to read Braille. That is pretty fascinating. All right, carry on, classmates. Have a good rest of your semester.